Hi everybody, hope you're doing well. In this lecture, we'll follow the previous one and we are going to calculate quantum dynamics of spin half now for real, because in previous lecture we just discussed basic facts about rotations and polymatrices, the connection of polymatrices with rotations. So now let's let us start from the Hamiltonian, which describes the interaction of a quantum particle of spin half with a magnetic field. All right, it, it could be a two-level system where there is a pseudo-magnetic field also, right? But for now, just let us restrict ourselves to a spin system, a spin half particle, right? Uh, we'll see later that spin half particles are fermions, but that discussion is beyond the scope of the present lecture. All right. So suppose that other degrees of freedom are already known or are irrelevant for the moment, and the only thing you need to calculate is the spin of the particle. All right. So this is the Hamiltonian. A magnetic field can be applied to an arbitrary direction, but suppose for the sake of simplicity, you're applying a constant magnetic field along the z-axis. All right. So if you have an xy plane here, x and y planes, the magnetic field is pointing outward of the board plane here, all right, of the xy plane. All right. So the magnetic field is pointing outside here from the board. All right. Now let us discuss a little bit more this system, because it's a very interesting system, and we will use some results from the previous lecture, of course. But look that for a vector in the z direction, the Hamiltonian reduces to this thing here, minus some constant of the particle, some constant which is the value of the magnetic field, and the polymatrix in the z direction. So of course, this is in the diagonal form. Of course, we have chosen the magnetic field to just put the Hamiltonian in already diagonal form for the sake of simplicity, right? But for complicate things, we will consider an initial state which is not an eigenstate of sigma z, all right? So just to make dynamics more interesting, all right? Now, there are two eigenstates, one corresponding to the up state, which in the basis which diagonalize sigma z is this thing here, right? And the other is the down state. Notice that the energy, the eigenvalue for the energy, the eigenvalues here are plus minus this constant here, and the up state corresponds to the lower level, which is the fundamental state. We are dealing with the particle of positive charge for now. It could be a positron, it could be a proton. Just you need just to change this constant. It's a constant which is a characteristic of the particle. And there is a down state here, and the down state has a plus energy value. So this minus compensates this one, and you have upper level of energy and a excited state. So if you draw an energy diagram, you'll find out the up state here, or the down state here, and the up state in the lower level. If you have a change of sign here in the Hamiltonian, of course, both energies are just interchanged, all right? And there is an energy difference here a gap between these states. If you look at this thing here, you can clearly see that if magnetic field is zero, both states have the same energy, right? There is no distinction in energy levels from one state to the other, and this is called the degeneracy. When you apply magnetic field, you just remove the some symmetries of space. The space is no more isotropic because the magnetic field is changing things, and there is a preferable direction for the spin to be directed. It's z direction, it's the quantization axis. And in this case, you remove the degeneracy, you lift the degeneracy, and the states become separated in energy, right? And there is an energy difference. So suppose the particle is at the fundamental state here, okay, at the bottom here, it's the fundamental state, and you can insert photons into the system of a proper frequency, and this particle can be just promoted to the excited state, to the, in this case, the down spin, the spin pointing downwards in the z-axis. Okay, so this frequency is related to the delta of energy. We can write it as h bar omega, and this corresponds to the difference energy, the upper state minus the down state, to get a positive result. So it's easy to see that's twice a constant, which is a property of the particle, multiplying the magnetic field. So the higher the magnetic field, the higher the separation of the levels, and the higher the frequency you need for the photon to promote electrons or whatever positrons to the excited state. All right. So you can just write this constant here for a given magnetic field as h bar omega divided by 2. All right. So you isolate this mu b0, just h bar omega divided by 2. So if you want to find out this constant, and you know already the value of the magnetic field, you just can plug into the system waves by varying the frequency. It's just how resonance machinery works. When you find the proper frequency, when the system resonates, you promote the particle to the upper level, all right, and energy is absorbed at a higher rate, and you can find exactly the difference in energy, and you can find the properties of a particle, for instance, because you already know the b0 and the omega you can measure by measuring frequency. All right, so that's just preliminaries on this quantum system, which is a spin half system. All right, so we can write the Hamiltonian in the following way. H Hamiltonian is negative of h bar omega divided by 2, which is the previous constant, sigma z. All right. There is a spinor which can be written as a two-component function. The up state and the down state, they are functions of time, of course. These are complex numbers, and these complex numbers can be solved for as time evolves using Schrodinger's equation. This object here, which is a two-component vector in Hilbert space, having complex numbers here, is called a Pauli spinor. I don't know if I mentioned that previously, but it's Pauli spinor. All right, so this is the object we are talking about. It's a polyspinor. And Schrodinger's equation, we have two ways of solving problems. One of them is Schrodinger picture, so Schrodinger's, and the other is Heisenberg's picture. Heisenberg picture. We will do both ways. All right, we will perform calculations in both pictures. So in this case, let us specify what we are willing to do right now. So the exercise or the problem is the following problem. Find the average of the components of the polymatrices for magnetic field applied in z direction, which you already discussed, right? So the Hamiltonian is already given, and initial state psi zero is a spin corresponding to the up state or the plus state in the x-axis. All right. So you have the z-axis here. You have the x quantization axis. Our magnetic field is pointing upwards in z, and our spin system this is the state psi zero. All right. So they are orthogonal for start. Right? This is the problem which we are willing to solve. Notice that this is spin precession because you can say that this is the calculation of the magnetic dipole moment average. And this is a vector, it can rotate in space. And this thing here corresponds to some constant. I'll call mu naught here, mu subindex 0, right? This is a constant of the particle, which corresponds to that value, so that constant, right? And the average in the directions of the Pauli matrices. We must remember that Hermitian operators always have real values for the averages. Okay, classical things in the correspondence limit are related to measures of averages or averages of operators, of quantum operators. Okay, so classical behavior is obtained by averaging over a large number of quantum systems. So you'll find a classical behavior if you pick a lot of these particles described by this Hamiltonian and you measure at any instant of time a lot of systems independent and exactly the same system at the same states initially and averaging over an ideally an infinite sequence of equal systems, you'll find the averages, okay? Because if you measure just a single system, a single one of these operators, you'll find out just an eigenvalue, +1 or -1 at any given instant of time. So these things becomes more classical when you produce equal systems. Suppose there are electrons of spin half. You prepare many electrons of spin half at same state, at same initial state, same conditions, and you let them evolve in time, and you measure all of them, and then you can average. So this is an average, all right? This is what we mean by average. And the average need to resemble somehow the classical world, all right? So let's do the math here. First, we'll calculate the Schrodinger picture, all right? Schrodinger's. So first, let's do Schrodinger's. But let me remember some facts. You can prove that. You can do that. Sigma x is just the matrix up, down, plus down, up. You can do the math. You can show that. This is just sigma x matrix, right? And sigma y matrix also have only components, off diagonal components. But in the end, you must produce this matrix here. So you have a up down, this object here, and the down up, this object plus I here. And the diagonal terms are 0. And also you can write sigma z in this form here, up, up, plus 1 in the diagonal, minus, down, down. It's minus 1 in the other value for the diagonal. It's in the diagonalized form. So we can do the math for that. Also, you can prove that sigma x applied to the up state produces the down state. So the sigma x matrix in the language of the z basis is a flipping operator. It flips the states of the spin in the z direction. So if you have an up state, it flips to the down state. And if you apply it to the down state, it flips to the up state. It's just the operation of the operator, all right? And sigma y, you can also do the math. It flips states, but a different phase factor emerges. Because if you apply this matrix to the up state 1, 0, it will produce the down state, but with the imaginary unit here. And if you apply to the down state, you end up with the up state with minus the imaginary factor here. All right, that's it. That's for the sigma x and sigma y matrices. I don't know if you can see it properly, but that's what we have here. And you can also look the results by applying this matrix. For instance, pick up the sigma y, apply it to the down state. So apply it to the down state, you'll find out the minus I, because the down state, when you apply this matrix, up state is directly projected to the down state here, 0, because of the orthonormality of the basis. And the down state projected to the down state gets, you get 1, and the up state remains here multiplied by minus the imaginary. And you can do that for all the components here. All right, so if you need to remember these things. Remember that the sigma y and sigma x Pauli matrices, when operating on the sigma z basis, it just flips states. This is very important. Also, you can write the evolution operator, the u operator here, which is just the exponential of minus I, the Hamiltonian divided by h bar, multiplying time t. The Hamiltonian here, just remember, is minus h bar omega over 2 sigma z. And in this case, if you plug in here, you'll find out exponential of the imaginary unit h bar omega sigma z over 2. Notice this kind of operator we already discussed in the previous lecture, and it's related to an angle of theta in the previous lecture, which corresponded to minus h bar omega, all right? So it's negative from previous lectures, if I remember correctly. But it doesn't matter, it's just multiply by t here. The h bar cancels out when you plug in here, and it's t to be precise, right? But it doesn't matter, it's just a rotation by an angle of theta. And we already discussed that Pauli matrices are related to rotations, and this is a rotation operator, all right? So you can solve in Schrodinger picture in two distinct ways. You can use directly the Schrodinger equation, which corresponds to the Hamiltonian applied, the time derivative corresponds to the Hamiltonian. So in this case, you would have a Pauli spinor, which corresponds to the up and the down components, which are functions of time, with the initial components already known. So psi up of 0 is equal to the psi down of 0, because our initial state is the up state in the x direction, right? So this is the initial condition, and you can write down the equations for the psi up component. Corresponds to multiplication of matrices here, but you'll find out minus h bar omega over 2. The up state is, in this case, very easy because the Hamiltonian is diagonal, but if the Hamiltonian is non-diagonal, you mix up these components, right? And you can solve for the down state with respect to time. It corresponds to the other component of the matrix, and this is non-coupled system of equations. You can solve it readily, all right? You can solve it. I'll do the math in another way, but you can just solve it. It's very easy. It's just non-coupled equations. But in general, if your Hamiltonian has non-diagonal terms, you'll find out that the derivative of the up state gets in the right-hand side of the equation, the up and the down states mixed. And same for the other equation, all right? So you do the math, you find out that. It's a special occasion, special case. It's just diagonal because the rotating operator is just sigma z, all right? It's already diagonal in its own basis. So we can apply the operator. So to obtain psi of t, we can apply the operator to the psi 0, which is the plus in the x direction. And in this case, we will apply this operator, which is imaginary, exponentially imaginary omega t over 2 sigma z, operating on the function which is 1 over the square root of 2 up state plus the down state. If you demonstrated the eigenvalues and eigenvectors of the sigma x matrix, you already know that the plus state in the x direction is just a linear combination of up and down states with respect to the z direction. And remember the following. When you apply any function, but in particular the exponential of a matrix to one of its eigenvectors, it's just a constant here, corresponds to the constant multiplying the eigenvalue corresponding to that eigenvector, and the eigenvector is repeated. So you can perform the calculations promptly here, because sigma z, and this is an eigenstate of sigma z. This is the matrix, this is the eigenvalue of the matrix, this is eigenvalue, eigenvector of the matrix also, and this way you'll find that function evolved in time corresponds to 1 over square root of 2. When you apply to the up state, you get the plus eigenvalue. So it's the exponential of I omega t over 2, e to the I omega t over 2. And when you apply to the other one, you get the minus eigenvalue. So they are just phases. Notice that the initial condition is already there, because if you put t equals to 0, this goes to 1, that goes to 1. But as time evolves, the phases evolve differently. This is a plus and this is a minus. And the phase difference between these two states, the up and the down state, in the linear combination, as time evolves, the phase difference goes to omega t, all right? So phase is a very important factor in quantum mechanics, right? So now we can calculate the average of sigma x, which corresponds to projecting out these things here. And if you plug in the bra here and the cat here, you just remember that 1 over square root of 2 comes from both bra and cat, and that's produce a half factor here. And you need to take the complex conjugate here, so find, just replace I by minus I. You need to do that. Okay, so this is the bra. 1 over 2 is because I already told you that. And we'll have this thing here. All right, so multiply this here. But when you apply the sigma x to both of these terms here, so applying this thing here, right? Applying this thing here to the up state, it will become the down state, all right? When you apply the sigma x to the up state, becomes down state. When you apply sigma x to the up state to the down state, it becomes the up state because it flips. It just flips. And now I can eliminate that from the equation because I already applied. So I have a down state here. I have an up state there, right? And now you can calculate the inner products. Up with down is 0, up with up is 1, down with down is 1, down with up is 0. So you find in the end the following: sigma x is equal to this projected onto that. You have a 1/2 here, e to the minus I omega t, because this minus I omega t over 2 picks that other factor here, and exponentials, you just need to sum up the phase factors. So this with that gives you twice this value here. Up with up projected gets 1, you get 1, plus this. The non-vanishing value is only when projected to that thing, and this is twice this value for the phase, right? Just remember, up projected with up gives you 1, down projected with down gives you 1, up with down are in the contrary, and the reverse sense gives you 0. So just the orthonormality of the basis. But this thing here, 1/2 of the exponential I omega t plus exponential minus I omega t is just the cosine of omega t. It's just the definition of a cosine. if you are in doubt, you can just write this thing, the complex relation. If plus here, if minus here, so the imaginary parts cancels out, and the the result will be twice the real part, but divided by 2, so you get the cosine of omega t there. All right, so that's it. Now you can calculate the same thing for sigma of y. Now I will use the same things here, so allow me to do that. Okay, so I'll recover previous things here. This will be up, this will be down state. I'll plug in sigma y here, all right? That's what I'm doing. So the 1/2 will be there, also will be there. When you multiply the sigma y by the up state, it goes to down state and vice versa. So this projected with sigma y projected with that gives you 0. The only possibility is this combined with that, because the sigma y will flip the state here to down state, and you'll find out an I omega t factor. There's a plus here, this phase factor, and another phase factor e to the minus I omega t. I just need to know what are the numbers and the sign convention here. But just look that when you apply the matrix sigma y to this thing here, you get an imaginary, and this is the plus, so you get an imaginary here. And when you apply sigma y to the down state, you get the minus imaginary, so you'll find out minus imaginary multiplying this thing here. All right, you can do the math, you can prove that a little bit harder if you do the math, but just a few more lines perhaps. And this thing here, you can use also the properties of sine. So this is the exponential, pardon, plus minus equals to cosine omega t plus minus I sine of omega t. And when you multiply imaginary by imaginary here, you get a minus sign. When you multiply minus imaginary by minus imaginary in the other factor here, you're going to get a minus sign. So twice the minus sign. The half here cancels out, the number 2. And cosine minus cosine multiplied by imaginary, it doesn't matter, just cancels out. So you'll find out minus sine of omega t here. All right. And if you do the math, you can also prove. I'll not do that. It's just easy to see, because the psi state at any given instant of time is just a linear combination of phase factors here, but modulus are kept unchanged by time evolution here. So you have 50-50 up and down, plus and minus. So in the average, the average of sigma z, or the spin in the z direction, is half up, half down. So it cancels out. Because of that, it's 0. And now look at the average of the magnetic moment, which is a vector, is just a constant multiplying the average of sigma x, the average of sigma y, the average of sigma z, and this is cosine, this is minus sine, and this is 0. All right, and this is just a spin precession. All right, I'll I'll try to make it clear. If you have here the x and y plane, notice that the average of sigma x is sine, the average of sigma y is minus sine of omega t. And in this way, the initial state of the system corresponds to a spin here in the x direction with magnitude 1, normalized, of course. And as time passes, as time evolves into the future, these things rotates and it becomes, when you reach pi over 2, of course, minus in the y direction, and then it rotates more and it gets negative in the x direction, then positive in the y direction, and it rotates. It precesses around the magnetic field, which is out, pointing outside the plane, right? So this spin rotates clockwise. It's a clockwise rotation of the spin. So this is called a spin precession. If you did the math for the classical magnetic dipole and solve the equation for field in the z direction, you'll see that you have a z component of magnetic field. There are no losses. It's a lossless system now. And this spin is pointing in the x direction, but it rotates. It precesses. And if you put a spin in another direction as an initial condition, the amplitude projected to the x and y axis would be lower than the unity, but the z component would become fixed, and this thing precesses, keeping the average of the z component fixed in time, but the x and y components just keep changing over time and rotates, the spin rotates around the magnetic field. That's why it's called spin precession. The axis of the spin is precessing around some axis. All right. So this is called the spin precession problem. Right. Next, we'll show the same thing using Heisenberg's picture. So in Schrodinger's, the state evolves, the averages are like classical things which I can measure, but the state evolves and the Pauli matrices are kept fixed in time for Schrodinger. But Heisenberg's is the opposite, all right? But the result must be the same. You need to have the same result. The results are independent of the picture. So now just remember that you need to, if you want to calculate commutators for Pauli matrices, this relation is valid, applies to Schrodinger picture. But also, if you redefine the matrices by a unitary transformation, you can show that this also valid in any representation. All right. So for Heisenberg, Pauli matrices are rotating somehow, but the commutation relations for rotating matrices still applies. All right. Now remember that sigma x for Heisenberg is just the sigma x transformed according to this equation. Sigma y for Heisenberg is the matrix sigma y transformed according to this equation. And the sigma z of Heisenberg is the same thing, same transformation applies, same operator. This operator here is just the imaginary omega t sigma z divided by 2. All right, it's just the Hamiltonian minus general, it's minus I, the Hamiltonian times t divided by the h bar. All right, so in this case, it's just a rotation. We already performed these calculations in the previous lecture, remember. But if you want to solve the equations by matrix algebra, you can think about the sigma x, sigma y, and sigma z of Schrodinger as some directions, all right? And then you can write the Heisenberg as a function of time as some constant, C1, depending on time, sigma x, plus some other function. It's not a constant, it's a function, sigma y, and sigma y of Heisenberg evolving in time is some constant C3, sigma x plus C4, sigma y, and you need to solve for these functions, these four functions here. All right, that's all you need to solve. And sigma z in a Heisenberg picture in this case, because you know that the rotations are performed with z components fixed, which means the axis of rotation is the z-axis. It's just sigma z of Schroedinger. This thing does not evolve in time. So you know that the x and y components are just mixed, but the sigma z kept preserved over time. If you have a magnetic field over directed in an arbitrary direction, you'll find out that you need some other constant mixing with sigma z here and here gets all mixed, and you'll have 9 components to solve, but some of them are related to each other, and you need to find equations of motion for Heisenberg and the operator. So the sigma x of Heisenberg, the time derivative of that component, is just the commutator of that component, the Hamiltonian. And the Hamiltonian is unchanged because the evolution operator which you are using commutes with the Hamiltonian, of course. So in the time-independent Hamiltonian, it's a valid scenario. So you need to calculate these things, and you'll find a derivative of the function C1 is connected to all the other functions here, and you'll find the coupled set of equations for these functions here. But we not do that. We will not do that way, all right? Because in this case, we already worked out the problem. So sigma x for Heisenberg evolving over time is just the U dagger, the transpose conjugated, which is the inverse in this case because it's an unitary operator, times the evolution operator U here, and you'll find out this is just minus I omega t over 2 sigma z sigma x into the I omega t sigma z over 2 sigma y for Heisenberg evolving in time. We already know that sigma z does not evolve because the axis of rotation is z, and this thing we already calculated in the previous lecture, but I guess now we have a negative angle theta is equal to omega t for the results we already found in the previous lecture. And now we'll find out that the sigma of x in the Heisenberg picture is just, when you perform a calculation there, you'll find out cosine of omega t sigma x plus sine of omega t sigma y. So this is the function C1, this is function C2, all right? And this is minus sine of omega t in the direction of sigma x plus direction is pseudo direction here plus the cosine of omega t sigma y. What is the advantage of this formulation here is that the operators evolve in time. You can calculate the average corresponding to any given initial state. All right, so you put the initial states here and you calculate for any given initial state. All right, so in the Schrodinger picture, you need to calculate the evolved state for a distinct initial state again. But by contrast, the Pauli matrices are just constant in time. So, but results for averages are the same, okay? And of course, sigma z doesn't evolve, right? Now we are interested in calculating this thing here. In Heisenberg picture, the matrix evolves, but the state is a constant. So you need to calculate this thing here. And also for the y component and for z component, of course, but this state is already known. And this state, in the case we are considering here, is just the plus state, is the plus eigenvalue in the x direction. So a plus state in the x direction can be considered as equal superpositions of y components or z components. You can show that. And in this case, when you calculate the averages, you calculate the average of sigma x at time t equals to 0 for if you are thinking Schrodinger's, and the average of sigma y, just two averages. Of course, the average of sigma z is the average of sigma z, which we already know. So this is 0, of course. But now, if you calculate the average of sigma x with respect to an eigenstate of it, correspond to that eigenvalue, and this is 1, all right? And the average of sigma y with respect to an eigenstate of sigma x is 0, okay? Then this corresponds to, when you put the plus state in the x direction here, you just find out the average of this, and it appears here and here. You'll find out that this is 1 and this is 0. So cosine of omega t minus sine of omega t. Of course, it's the same result as previously, as in Schrodinger picture. It doesn't change because you change the viewpoint in quantum mechanics. So Heisenberg and Schrodinger produces the same result. And of course, interpretation is the same. In classical terms, it is a spin precessing around the axis of a magnetic field, right? So this is it. For spin precession, that's it. A more involved problem which we are interested in and we'll calculate in, in next lectures, is a temporal evolution when you uh, when you apply time varying magnetic fields, because right now the magnetic field is just a constant. So next steps in this problem would be consider a magnetic field which has a z component which is constant in time plus some transverse components which are functions of time. All right? So this will be the field which lifts the degeneracy of the system, and this will be representing the radiation field which inserts into the system photons with the given frequency, and when you got lucky, the photon frequency is well adjusted to the resonant frequency of the precession, and this field will be absorbed and will induce transitions between up and down states. In the resonance, this occurs at a higher rate or a higher probability, perhaps, and that's the main problem of magnetic resonance. All right, you need to insert photons, in this case by magnetic fields, and this magnetic field has any frequency, but when it's matched to the frequency, the natural frequency of the system, which can be controlled by this magnetic field, you'll have many photons being absorbed by the system. All right? So I hope you could understand what I am talking about. I hope you enjoy the lecture, and see you next time.